In the last video, we wired Mem0 into DSPy pipeline and showed memory search, store, and reuse on local Ollama stack. This video is part 2, the CrewAI pipeline. Same Mem0 brain, same Chroma store, but now two CrewAI crews run in identical course building tasks. One with memory, one called without memory. And we measure the gap life, tokens, latency, projected cost, and whether the crew actually remembered a syllabus decision from many tasks earlier. Every CrewAI token count comes from get token usage summary. Deep path is exactly 2 LLM calls. Fast path is exactly 1. Deterministic head-to-head on a dashboard you can watch while the race runs. So I will walk through the code, starting with the config.py. I will start with the one function that connects CrewAI to everything else, which is the build crew LLM in config.py. It takes temperature defaulting to 0.2 and max tokens defaulting to 1200. The first thing it does is import CrewAI's LLM class inside function body, not at the top of the file. That's deliberate. Importing config on its own shouldn't drag in the whole CrewAI framework unless I'm actually building a crew. Then it retains CrewAI LLM object. The model is Ollama / followed by the chat model, that the same model name the rest of the demo already resolved from whatever Ollama has loaded. The base URL is the same Ollama endpoint. Temperature and max token are passed straight through. Now for the workload, we have the task.py in the crew folder, crew module. This is a list of jobs the crew is going to do, and the way it's built is the whole trick. At the top, there is a small data class called work item. It has 3 fields: task ID, which is a short stable name I store things under and show on the dashboard; the task text, which is actually instruction I sent to the model; and last field is depends on, which a list for the earlier deliverables that we need this task to stay consistent with. Then there is a list itself, work items, and the tasks are built on each other. The first one is a syllabus. It defines a 6-week course on transformer attention. Each week gets a theme and a core skill. Everything after this point back to it. The second is a module outline for week 1, and it depends on syllabus. Then a quiz bank and a lab guide, both depending on that module outline. Then a grading rubric. And notice it depends on the lab guide because the instruction literally says that the rubric must grade exactly what the lab asks student to produce. Then misconceptions tied to the week 1 themes. On FAQ, that depends on both the syllabus and the lab. And finally, capstone project that depends on the syllabus and the rubric. It has to reuse the exact week themes and the exact proficiency levels. So this is 8 tasks where the later work is only correct if you remember the earlier work. That's a perfect setup for comparing a crew that has memory against one that doesn't. And then, separate from that list, there is a recall probe. This is the one I use for a big finish. It asks the crew to state the week 3 theme and its core skills from the syllabus it defined earlier. And then design one in-class exercise for the theme without redriving everything. That last part is a trap. A crew with memory just looks it up. A crew without memory has to guess and it drifts. Now we have the shared brain.py. So this file is the engine. It's where task actually gets run. Right at the top before CrewAI is even imported, I set 2 environment variables to turn off CrewAI synonyms, telemetry, and its open telemetry tracing. I use set defaults. So if I had already set those myself, my values wins. I'm only providing a default off. This just keeps the recording terminal quiet. Then a constant fast pass min hits set to 2. That's the threshold. If memory gives me 2 or more relevant hits, I trust it enough to take the shortcut. Fewer than that, and I do the full work. Next are 3 system prompts, one for each role the CrewAI can play. The planner prompt is a circular planner that turns a task into a tight, concrete plan. The writer prompt is a course content writer that produces the actual deliverables. And the reuse prompt is an important one for saving. It tells the writer it has access to prior work. It should reuse known material where it can, and it should never redrive something that's already been decided. That wording is exactly why the fast pass costs fewer tokens. Then there is a data class, task result, that holds everything one task produces. The ID, the output text, total token, prompt, and completion token separately, the number of LLM calls, the latency in second, how many memory hits it got, and the path label that's either fast, deep, or no memory. Now the class itself, shared brain crew, the constructor takes a user ID and agent ID. That's the identity that the memories are filed under, a top K for how many memories to pull, and a max token. It saves those and it builds one CrewAI LLM using the build crew LLM function I just described earlier. The first method is search memories. It calls mem0 search with the query filtered to the CrewAI's user ID and agent ID limited to top K. The second method is format memories. It takes the memories and turns them into a short bullet list block of text to drop into the prompt. The Y brain, this is the amnesia button's actual muscle. First, it tries to count roughly what's in the brain by searching, so it can report how many it removed. Then it calls mem0 delete all, scope to the cruise user and agent ID. Both of those are wrapped in try except, because if I hit the wipe button when the brain is already empty, it absolutely must not crash the run. Next, the store method, one call to mem0 add, saving the output under the cruise identity with metadata. Now the measurement method, the underscore call method, this is where measured, not estimated, actually happens. It asks CrewAI for its token usage summary before the call. It makes exactly one LLM call, passing system message and user message. Then it asks for the user summary again. And it returns text plus the difference between after and before. And finally, run task, which ties it all together. It starts a timer, then it branches. If this run uses memory, it searches, formats what it found, and record the hit count. If it doesn't use memory, then the called crew, it just sets the no one context to no prior memory and 0 hit. Then there is a tiny helper that accumulates prompt tokens, completion tokens, and calls, so both paths report their totals the same way. Now the routing decision, if this run uses memory and it got at least 2 hits, it takes the fast pass, one single call with the reuse prompt, handing the model the task and the known memory and telling it to add only what's missing. The path is labeled fast. Otherwise, it takes a deep path, first planner call to produce a short plan, then a writer call that takes that plan and produce the final deliverables. 2 calls. The path is labeled deep if this crew has memory turned on, or no memory if it is the called crew. Then it stops the timer before it stores anything. The reasoning is that in real memory, writing to memory is background bookkeeping, so it shouldn't count against how long the answer took. Only after stopping the clock, it stores the result, and only when both use memory and store are true. That flag is how the recall probe later runs the memory crew without polluting the brain. In the telemetry control.py, we have a small file, but it solves the real problem. The dashboard and the running race are 2 separate processes. If both of them try to write to the memory store at the same time, I could get database lock or corruption. The rule is only the race process ever touches mem0. The dashboard can only ask for something to happen. There is one path at the top, a small JSON file in the data folder that acts like a mailbox. The first function, request amnesia, is what the dashboard buttons calls. It makes sure the folder exists, generate a short unique ID, writes the ID and timestamp to a temporary file, and then rename the temporary file over the real one. The rename is atomic. The reader can never catch a half-written file. It retains the ID so the dashboard can show confirmation. The second function, pop amnesia request, is what the race process calls on every loop. If there is no file, it returns nothing. If there is, it reads the ID, and it only returns the ID if it is different from the last one the race already handled. That's a debounce. The request fires exactly once, even though the file sits there. And if the file is somehow corrupted, it just returns nothing safely. So in the workload, I added the crewrace.py file. This file is the one behind the demo crewrace command and the thing that actually runs on our demo. The main function run race, it takes the number of rounds paused between tasks and max tokens. It starts by minting a session ID and resetting the life matrix for the clean run. It builds one shared brain crew that both crews will share. It sets up a dictionary to remember each task's memory output, a variable to track the last amnesia request it handled, and an iteration counter. Then the main loop, which runs a number of rounds, and inside that, over every work item. At the top of each task, it checks for amnesia request. It asks the control channel whether there is a new wipe request. If there is, it wipes the brain right there because this is a process that owns the memory handle. It drops marker on the dashboard at the current position, records that it handled the request, clears the request file, and prints what happened. Then it runs the tasks twice. First, call crew with memory turned off and storing turned off. That's the baseline. It never touches the brain. Then the memory crew with memory on and storing on. It saves the memory crew's output into the dictionary keyed by task ID so it can be used later as the reference for the recall prop. Then it logs pair, the session and the iteration, the task, the framework name, CrewAI, and both sides. So we have it remembered moment after all the cycles being finished. So it grabs the syllabus output it saved earlier as a reference. If that exists, it pumps the iteration and runs the recall prop twice, once called, once with memory, and notice both have storing turned off because I don't want the prop writing into the brain. It scores the two answers against the real syllabus using the score recall, logs the consistency prop to the dashboard and prints the scores. Finally, it marks the run complete, which flips the dashboard status to complete. For the command, it's the same like part one. So we have the demo reset and the demo dashboard command that we can trigger it to see the dashboard at the start of our workload. Then we need to run the demo crew race. You can watch at the top of the dashboard, the session ID spins up, something like crew underscore an ID numbers. Status is running, framework filter shows CrewAI. The odometer at the top are still near zero. That's expected. So round one is expensive for both sides. The brain is empty, memory crew searches, finds nothing useful, fall through to the deep path. Planner plus writer, 2 LLM calls, and the called crew always deep. So the cyan and rose line on the cumulative charts clamp together. So here you will see always pairs, variant no memory, path no memory, 2 LLM request, then variant memory, path deep, always 2 requests. Memory hits low or zero. The memory crew is writing deliverables into Chroma, syllabus, module outline, quiz bank, but it hasn't learned enough to skip work yet. So in the second round, when the second round starts, we can see the same tasks again, but now Mem0 returns hits in my run, 20 hits per task. Once the brain is warm, path flips to fast and 1 LLM call instead of 2. So look at the cumulative tokens chart, rose line, called crew keeps climbing at the same steep slope. CN line, the memory crew bends. The gap widens with every task. That's not projection. Those are measured tokens from CrewAI's usage summary. So when the run completes, status flips to completed. Now read the odometers. In my session, few thousand of tokens has been saved, a few cents has been saved, and the cost and all of this, as we mentioned, experimental, and we are calculating the tokens from our CrewAI orchestration layer. It's small in local Ollama, but the percentage is the point. 30 to 40% token reduction on identical work, and also a couple of 100 seconds being saved. So the memory crew did the same course building work and spent third less tokens doing it on a hosted frontier model. That line item shows up an invoice. If you want drama, hit the wipe memory now in the sidebar. The dashboard doesn't touch Chroma, it drops the request file. The race process wipes the brain between tasks. A dashed wipe marker lands on the cumulative chart. Watch what happens next. Memory hits collapse, path falls back to deep. The CN line accelerates, catches up toward the rows, because the crew lost its brain mid-race. Then, as it stored deliverables again, fast path comes back and the gap reopens. So what did we learn with CrewAI specifically? The first thing, Mem0 is not a CrewAI plugin you bolt on. It's a routing layer. Enough hits and your crew skips a full plan and writes cycle. 1 call instead of 2, that shows up in real token count, not vibes. The second thing, if you want to demo or benchmark savings, control your call path. The crew executor is powerful for production orchestration, but for measurement on a local model, explicit LLM.call step give you a clean baseline. The third thing is that memory buys you consistency across session and tasks, not just the speed. The recall probe proves the crew still aligns with the syllabus decision from many steps ago. That's what you want in a course builder, a support agent, or operation runbook. Anything with recurring deliverables that must stay aligned. The fourth is observability. So observability makes it real. Race pairs, cumulative charts, amnesia mid-run. You can show stakeholders why shared memory is infrastructure, not a nice to have anymore. Thanks for watching. If you want more of this, like the video, subscribe with notification on, and share it with your friends. We release new videos every week on AI development, agents, and developer tooling. Thanks for being here.